Hey everyone! Today, we're going to crack one of the most classic coding challenges out there. But don't worry, this isn't a test. Just think of it as a fun logic puzzle that we're going to solve together step by step. Okay, let's just forget about code for a second. Imagine you're in a room and it's just filled with numbers. How would you find the one other number that, when you add it to yours, makes a specific total? How do you find that perfect pair? Well, that basic idea is the heart of the mystery we're solving today. So go ahead and put on your detective hat because you've just been handed your very first case, the two-sum challenge. So here's our case file. We get a list of numbers. You can think of them as our suspects. And we also get a target number. Our mission is to find which two numbers in that list add up exactly to our target. But here's the twist. We don't actually want the numbers themselves. We want their positions in the list, what programmers call their indices. Let's look at some evidence to make this super clear. Our list of numbers is 2, 7, 11, and 15, and our target is 9. Right away, you can probably see that 2 plus 7 equals 9, but remember, we need their positions. In programming, we always start counting from 0, so 2 is at position 0, and 7 is at position 1. And boom, that's our answer, the list 0, 1. So how do we actually find this pair? Well, the first thing that probably pops into your head is to do some old-fashioned detective work. Just be really methodical and check every single possibility until you find what you're looking for. This method is called brute force. And yeah, it's pretty much what it sounds like. We'd pick the first number, 2, and then just add it to every other number. Is 2 plus 7 our target? Yep. But if it wasn't, we'd check 2 plus 11, then 2 plus 15. If we found nothing, we'd move on to 7 and do the whole thing all over again. It's thorough for sure, but man, it's a real grind. And this grinding method has a really big drawback. It is incredibly slow. I mean, it's fine for 4 numbers, but imagine a list with just 100 numbers. This approach would force you to make almost 5,000 different comparisons. A good detective is an efficient detective, and we just know there has to be a smarter way to crack this case. And of course, there is a better way. It's time to introduce our secret weapon, the super-fast evidence locker. In the world of computer science, this is called a hash map. Basically, it's a special kind of list where we can store and look up information almost instantly. It is going to completely change how we solve this problem. So what makes this hash map thing so special? Well, think about it like this. Searching a normal list is like trying to find one specific word in a book by reading it from page 1, page by page. A hash map? That's like using the book's index. You just look up the word, find the exact page number, and jump right there. It gives you an almost instantaneous lookup. All right, now that we're armed with this awesome new tool, let's restart the investigation. You have to see how our smart detective solves this entire case by looking at each number just one single time. We start with our first number, 2. Since our target is 9, the other number we need to find is 7, right? Because 9 minus 2 is 7. So we check our evidence locker. Have we seen a 7 before? Nope. Right now the locker is totally empty. But, and this is the really clever part, before we move on, we take the number we just saw, the 2, and we log it into our evidence locker. We report the number, 2, and its position, 0. Think of it like leaving a little breadcrumb for ourselves. Now we can move to the next suspect in the lineup, the number 7. Okay, we're at number 7. We ask the same question. What number are we looking for? Target 9 minus our current number 7 equals 2. We need a 2. We check our evidence locker and, aha, there it is. Our hash map, our super fast index, instantly tells us, yes, I've seen the number 2 before. And I remember it was at position 0. And just like that, case solved. We have our current numbers position, which is index 1, and we have the position we just retrieved from our evidence locker, index 0. We found our pair, and we did it by looking at each number only once. How cool is that? Now, solving the case is great, but a top detective always reviews their performance. So let's have a quick debriefing to understand exactly why this new method was so much faster. And this is where we get into a really cool concept called efficiency. Let's compare the two methods. If our list has n items, the slow detective's work grows exponentially. We use a rating system called Big O notation to describe this. The slow method gets a rating of O of n squared. Our smart detective, who only passed through the list once, gets a rating of O of n. And as the list gets bigger, the performance gap between these two is just astronomical. This rating is called time complexity. Think of it as a grade that describes how an algorithm's runtime scales as the input size grows. An O of n algorithm is linear. If you double the list, the time roughly doubles. But an O of n squared algorithm is quadratic. If you double the list, the time quadruples. That's why O of n is kind of a gold standard we're aiming for. But there's really no such thing as a free lunch. To get that amazing speed, we had to use our evidence locker to store clues, and that takes up a little extra computer memory. This is called space complexity. And this highlights a fundamental concept in programming, the time-space trade-off. We often use a bit more memory or space to make our programs run much, much faster. Okay, you might be thinking, this is a neat puzzle, but why does it matter so much? Well, the answer is that this simple problem teaches us some of the most fundamental concepts in computer science. It really is much more than just a puzzle. Understanding two-sum is absolutely foundational. It's a pattern you'll see again and again as a building block inside much harder problems. It's the perfect illustration of that core trade-off between time and space. And most importantly, it shows that choosing the right tool for the job, in our case, the hash map, is everything. And hey, a little inside tip, it is one of the most popular questions asked in technical interviews. If you take one thing away from this, let it be this. Good programmers can solve a problem, but great programmers solve it in the most efficient way possible. That's the real art of what we do. And with that, this case is closed. You've learned how to find a pair of numbers efficiently. But here's a final question to think about. What if the challenge was to find 3 numbers that add up to the target? How would you adopt your strategy to solve that case? Thanks for tuning in.